So, the first thing is done, and this is all done by Gibbs. NVT, that means energy is the first thing, because it is all natural that a system will exchange energy with the surroundings. So, that goes to give you. So, then Gibbs did this amazing, he must have a very clear idea of what was going on. It must have been very, very interesting, because if you think of it, there is a man alone sitting in Starling laboratory in Yale. He once went to Europe, came back, then rest of his life he never left. Many people gave him offer, but he never left. Didn't marry, and in the morning they used to go like Immanuel Kant, of the great philosopher in Germany. He used to, in the morning, used to go to his laboratory, and in the evening he used to come back to his home. All his entire life he lived with his sister, who took care of him, and that is it. But those were very common those days, this kind of people, like kind of ascetic, highly ascetic and dedicated life. So, there sitting there, he must have this huge clarity of vision that how to go. So, the first clarity and brilliant idea was to go to the ensemble, because I give you my again and again the example of the 10 water glasses, they are all in different microscopic states, but their properties are the same. So, that would give you the idea of creating an ensemble, because in one stroke he went from solving Newton's equation to a distribution function. That was the whole idea of ensemble, that you go to distribution. As soon as you go to distribution, you can define averages. As soon as you can define averages, you can start doing calculations, analytical calculation. Otherwise, you are stuck, you cannot solve the 3-body problem. Okay. So, that was the brilliant beginning of the whole of statistical mechanics, this ensemble. Then he made those two hypotheses, and there was time average equal to ensemble average, I have explained many times. Follows from the concept of phase space, which I think I did in second class or first class. Now, then he had to make equal a priori probability, because there is all his microscopic states have the same energy, and there is nothing that we know about them other than that, they are the same energy. So, there is no other option than to assume they are equal probability. So, there comes the equal probability, but then he landed in trouble, because his ensemble is now taken care of. But who guarantees that the time average equal to ensemble average, the first postulate? Because for doing that, my system, one system, that has to go through all the microscopic states. So, then all the microscopic states must be visited. So, the concept of dynamics or time dependent came into ergodic hypothesis. That is why there is a huge school of mathematics even today who are working on ergodic hypothesis. And a realistic system was shown to be ergodic first time by great Buinovich and Sinai only in 1982. They said that a billiard ball or model or rather two-dimensional discs are ergodic. That is the first time by showing the diffusion exists, and the main thing is that two trajectories starting together go over all the space. You might have heard the beautiful things like chaos and Lyapunov exponent. All these things come from these are the part of these ergodic hypothesis and chaos, and that is why so much interest in chaos. Okay. Now, coming back, so when you go from relax the constant of energy, then again I do not have any next step to do. That is what I am saying, he must have a huge clarity of vision, because only thing that we have is this thing. So, what does he do? He said, okay, my picture here on the board, I put all these members of my ensemble, all the members of my canonical ensemble, very carefully listen, all the systems in my canonical ensemble who are exchanging energy with the surroundings, I put them against each other and then put them in a bath. Let them attain this humongous, this is my super system. My humongous system now equilibrates at a constant temperature, but they are exchanging energy. So, all of them are at different energy states. So, this now becomes my one super system. Now, I make an ensemble of this super system. So, this super system is now isolated completely after initial bath. So, this has a total energy, this has a, I hope you get the picture now. So, now I do a super ensemble of my super system, but the super system is now characterized by constant number of particles with total number of systems in my canonical ensemble, which part is super system, multiplied by the number n each, similarly volume, similarly the total number of particles. So, there are constraints. Now, I now want to write down. So, this is the distribution I discussed last time, that how this was the one we considered in microcanonical ensemble. In microcanonical ensemble, I have only a system has a microcanonical ensemble where a system is characterized by 4 energy levels and energy. So, n equal to 4, V does not come here, though V enters through given these energy levels. I hope you understand, like in particle in a box, do you remember? N square H square by 8 ml square, L is the length. So, energy spacing comes through. So, these are the, and I have 4 systems. So, this is my microcanonical ensemble, and microcanonical ensemble, this will my omega equal to 4, okay, alright. Now, I allow it to have different energies. As soon as I do that, these different states become available to it. So, a microcanonical ensemble has many more states available to it. Now, immediately we realize, okay, not all of them will have equal probability. So, now I need to find out how to talk which is more probable, which energy is more probable, and that is now done by saying, okay, n is the number of particles in system J, and add over that you get the total number, total energy in my super ensemble. So, n, remember, n is the number of, again, n is the number of particles in energy state Ej in my super. It is a bit because there is a 2 layers that we are doing here. These are number of systems, n is the number of systems in energy state Ej, okay. And then this is the Bayer combinatorics, and but that has to be, these combinatorics has to be maximized with this constraint. So, this is the constraint, and I can define now the probability. So, what I was asking the question, what is the probability? Now that all the energy levels are allowed, what is the probability? Now, what will be the condition that will determine what energy state is most probable in the system? So, I have removed all the barriers. A system can be in different energy states. I have still the constraint of number and volume, and in a super system, a super ensemble I have constructed. What is the condition that will tell me what energy level, what is the probability of a given energy level? Now, energy levels are allowed, energy levels are allowed. So, what is the condition that will dictate? No, that will come, that is the outcome. But without doing Boltzmann, you will take a guess, very simple. It will be the arrangement which will maximize the, which will maximize this. This is an amazing thing, that really amazing, and even now it never fails to surprise me, that this holds with enormous accuracy, 1 in 10 to the power 23 or probably whatever that kind of number. This law of maximum entropy, law of the maximum number holds such accuracy. It is just amazing that, because these are called laws of large numbers that come into play. So, by the time you have some 100 particles or 1000 particles, amazingly this distribution kind of, there is a force constant, of course, we will discuss that kind of zooms in, and it is essentially connected with a very deep level the stability of the system. And that is why statistical mechanics gives you a real insight into natural systems, that how things work, and it is really mind boggling if you think of it. Okay. So now I can define the probability of my system in a energy level and that is probability is Pj. That's why I asked that question, because I am going to go for Pj and only principle I have is maximize entropy. So I will maximize omega. So this Nj is the number of systems in energy level Ej, and now that particular energy level, my system can be my ensemble, super ensemble can be distributed in the omega ways, and so then this is the normalization. This defines the probability Pj. Take a look into that. It is not difficult. But I am saying we are looking at a higher level, and when I go to grand canonical ensemble, even another higher level will come. But this is resting on microcanonical ensemble. Grand canonical ensemble is rest on canonical ensemble. Okay.
Because that will give you the average number.
This would then okay, let us say what we are trying to say. Omega is the number of ways I can like here omega is the total number. They might be the same, though let me work it out. So this is the, in this case I say it should be 440. So given an energy Ej, I have a number of ways to define omega j. Alright. Now, so I now come there, I said it has to be weighted by omega, which is the, so the omega Nj given the weight of the, so in probability how do we go about? We go about, we define a probability by, I did discuss little bit in lecture 2, probability of statistics, which is given in my book in I think second chapter itself. You have the concept of the phase space, sample space. What is the sample space? Sample space is the total number of space that is available to you. Like if I toss a coin, then the sample space is 2, head and tail. If I throw a dice, then I have the sample space 6. Then it is the total number of the sample space, that is. So here the sample space is defined by total number of microscopic states that is available, not the total number of systems. Okay. So you remember the Venn diagram we draw, so that is the reason this should be omega. Okay. Is it clear? It is a good question. Now we have to go, what we did now, we have to do Starling's approximation, you know, omega ln n prime ln prime, and if you do that you get this quantity here. This is the thing that we have to maximize, but we have to maximize with this constraint, and then we do Starling's approximation, and we and after and we have the very important thing is, which I would love, but it would take one class, is the method of, this is called method of constant variation, method of Lagrangian multiplier. It was done by Lagrangian, where we found out that so it is essentially say that you are maximizing something, but you put a constraint to it, and for example you want to have a certain distribution, but you put certain conservation condition of the distribution, and these are the conservation condition. Now the way that Lagrangian multiplier goes is to put the constraint in the following form, so that you can see very easily that this is this condition. If I take dni with respect to that, then that variation, since this is a constant, this will go to 0. This is constant because total number of energy, because that is my super system. Super system is a microcanonical system that has a constant energy, so that will again be 0. So the way the Lagrangian multiplier works, that you put the constant in the following form, that the whole thing is, so this is the one you want to maximize, but with respect to this constraint. Alright, in the book, in the appendix I have described little better. Okay. So when you do that, we get this equation you can do it, go over, because this quantity is this quantity, and you can take the derivatives and then you get this is the condition. Taking the derivative, this equation 17, then you get the 18 comes out. This is actually easier of the things that we have done here. And then you can easily see that I can take some, this is the distribution that comes out, because just I have to take ln of that, and this that comes out, I sum over this. So star is there to denote that this is the most probable distribution, and this is what I was telling, that it works, though it is the most probable, it works with amazing accuracy. So I sum over that, I get the total n, and then the e to the power alpha is e to the power minus beta n. There should be actually n in front of it. I do not know why the n disappeared, and then Pj probability is this by n, and then this is so sum over n, the sum over this is capital N. So then e to the power, so probability is, so this is the probability, that this what the probability that you were telling, that Nj by total number of states and total number of systems in my microcanonical ensemble is this thing. Okay. So you get now, this is the probability of getting my system in a jth energy state. So Pj, J is the index of the energy state. So Pj is the probability, and this is what you recognize. Two things: A, this is the our Boltzmann, but we have not yet proved that beta equal to 1 over kBt. Beta is just in a constant parameter here. That is why it is called method of undetermined parameters. At that level they are not determined, they are introduced at constant, and we have to determine them with the time. So, and this is the quantity that comes here as the normalization is the partition function. This is the one of the most important quantity in equilibrium statistical mechanics, but this is just e to the Boltzmann factor, but sum over all the energy levels. So total weight is the, this is equivalent to omega, exactly equivalent to omega, but this is a canonical ensemble, where the difference between this microcanonical ensemble is that here I have all these different things, and in microcanonical ensemble I just have omega, total number of states, but in canonical ensemble each of these states are weighted by beta. So they are weighted by beta, and that is this is the weight. So I just do not have the states. Now I can also have a degeneracy here, but that we will discuss later. So this I am not going to do. So then now the most important thing, which I think we will just do a little, then probably stop, because I think these are how long this kind of heavy class can go on is there. So what the next thing is that, so we have the following, this is microcanonical. So then the way we write is N V, this is a common way of writing the microcanonical ensemble. All the energy levels, you can have 1 or 0, does not matter. This is determined by V. Okay. And so very interesting. So temperature will show that beta is 1 over kBt, that temperature comes through that, and total number of particles, energy levels is determined by the volume, and total number of this quantity is a lot of interest and a lot of insight can go into that, but I will discuss that a little later. So what do we need to do now? To show two things we need to do. A, that we have to establish the thermodynamic, how thermodynamic, like we have done, how thermodynamics follows from entropy. That was easy because we knew these things. We once this entropy, of course we have to establish entropy by correspondence with Euler equation and the relation omega, but once we have that, we know how to get temperature by dsD is the temperature, that is a well known relation. Then we know the temperature expression of pressure from entropy, expression of chemical potential from entropy. It is not the way you usually think about it, but microcanonical ensemble gives you those relations. Now we have to define similar relations from the similar relations for the in the canonical ensemble. So that is the idea now. So we start with the average, defining an average energy. So this is the average energy that comes out of my partition function of my distribution, and distribution is Pj. Pj is the probability of the system in energy level J. So this is the energy of the Jth energy level, and this is Pj. And then this is the standard definition. If this is the probability, this is the probability, then I have the partition function again. So partition function Q is actually measure of the sample space. So all the averages will be determined with respect to this, is the total weight of the sample space. So just like entropy omega is the weight of the phase space of the system, and all our averages are calculated with respect to this quantity. In canonical ensemble, this is the weight of the system. So a system characterized by NVE has a weight. That weight is given by entropy, or rather given by omega, and then log omega is the. Similarly, in canonical ensemble, this is the weight of the system. So that is the way to talk of partition function. It gives a weight of the system. That is why we maximize the weight or minimize the weight, alright. So now we then again play the, it is a very interesting trick here that I will probably not get to do fully, but dE trivially from here to here. Now as I said, there one now uses a very nice trick. Nice trick is that we use the definition of Pj, and then Pj is defined by e to the power minus beta Ej by Qj. So dPj is then written as, I can take d of the left hand side Pj, then I get these two terms. So ln Pj, so Ej on the other side is in the numerator, the exponent. So this is in the exponent. So I can take d of that differential here. So then this comes out, and then I get a, okay, no, I take log first, then I took the differential, I take the log. So ln P, E comes out, beta E, and become, so beta E ln Q. So I have a expression for E that I put it here, ln Pj by ln Q, then dPj comes dPj, the differential will come later. Then I have this term, I write Pj as d dVj, and then we know the condition that sum over Pj is 1, because it has to be somewhere, because this is probability of being in energy state, I add over everything, that is normalized, that is also come from this definition earlier. Tell me if you have any problem, and if that is so, the sum over dPj is 0, because I take dPj is 0, this is a thing we use constantly. Then we go back and we use the, the relation between entropy, which same as this relation, Kb ln Pj ln Pj. You know this? Do I have to explain this or not? Yes or no? Okay, this is okay, but tell me if there is okay. So this is the thing, actually what happens, this same as this, because if all microcanonical ensemble all are same, then you put, this is what some information entropy and all the things, but they are all the same in this kind of setup. So if Pj is 1 over omega, then 1 over omega, then then all of them come out, but sum remains, that gives omega. So this 1 over omega cancels that omega, and then this then 1 over omega is minus, I think I did that last class little bit, ds equal to kb ln omega. Okay. So, is it kind of a same generalized of these things to the energy levels, and then I can use this, do the ds, this quantity, and I get this equation. It is one can work it out that you get how these things work. Ln Pj, it becomes Pj, but I do not know why I did that, dPj, Ln Pj dPj. These equations can be, so these two equations I believe D as this can be combined to, you can get this, okay, entropy is now written as ds equal to d plus pdv, okay. So this is now Pj get cancelled, I have sum over dPj, and sum over dPj I just showed is equal to 0. So this term goes to 0. So I have left with this thing, right, and ds equal to d plus pdv, okay. So now I found this, we compare and we, so till now I have these things 1 over beta equal to d ln Pj dj, and that is now, so from here these terms, from here this term comes, and that Td we compare with Tds into Pdv plus Pdv. Then the first relation with thermodynamics is Tds is 1 over beta d ln Pj Pj. Yeah, 1 over beta. So this, so ln P, this is Pj ln Pj. So this term is okay, ds equal to d plus Pdv is okay, right. So here we have d Pj ln Pj, this quantity, and this quantity become ln Pj, this goes to 0, and then let us stop now, we'll continue from here. I myself have a little confusion what has happened here. So we'll start at 4 o'clock from this equation. Just no, at the end of the day, you are defining. So what is this here? Let me describe this little bit. So as I was telling, I forgot his name. So I have a phase space, okay. And what is the phase space? As I explained, that the total number of states in the system is a phase space always. Now that phase space is now partitioned into the total space now constitutes, say I for example bias my coin. If I bias my coin, then I can make head and tail becomes different. And then there are two ways, now look into it, that the biasing that I do, that probability has to add to something. That is my sample space, okay. That is the question he was asking, that is also equal to total n. In this case it will be 2. So but by biased probability, that had to add up to 1 also, total number of space. So here this quantity is the giving that total number of. So I have this, I have partitioned my system, which is given to me, that all the different energy levels, I have partitioned my whole system in my configuration space. So all different energy levels are there, okay. This is my sample space, and each of them, given by microcanonical ensemble, because all of them is constant energy. So exactly, yeah, exactly. So this is now, these are my microcanonical. So I finding for each of them omega. Each of them are finding omega, but now, so this is an energy level, say E1, say 10, this is 12, this is 14, all this. So I say now go, okay, if I give you energy level 10 in my diagram, how many ways I can do it? That is this omega, this small, this omega. Right, so now look at this, so this partitioning, so now I have to add up all the counts that I get here, and that my total, I have to get the total sample space like in Venn diagram. That total sample space is this quantity. Now I have to go back and say, okay, this has a way, this energy 10 has a number with it, which is number of ways I can do 10 in microcanonical ensemble. That quantity is this quantity. Okay. This is very neat and clean. Where the StatMac part is very clean, where one tends to get confused sometimes when the interface with thermodynamics comes. Because I always think that statistical interface is still a little rugged. There is always a little approximation that is made there. So that is where little bit ambiguity sometimes crops in. So we'll meet again at and we'll start from the thermodynamics part and D plus PdV at but so we'll finish canonical ensemble and start canonical today. Tomorrow we'll do hopefully tomorrow we'll start doing the fluctuations, at least half of towards the end of tomorrow morning. That's the most interesting thing. In my book, in the initial title, I have realization of promises that statistical mechanics has, see, difference from quantum is StatMac is the following. In quantum, I do Schrodinger equation, no derivation is required. Then I say decide E go to 0, I have H equal to EC. H I write down P square by 2m plus Vx. Then that's a differential equation. Now I put it in a Vx equal to harmonic oscillator, I solve, I immediately get experimental observable quantities, which is the vibrational spectroscopy, the lines. If I make a little distortion because of rotation, I get what is Q or branch, which is exactly experimental. Similarly, you do particle in a box, you know you go to conjugate polymer. So at a almost trivial level, you get results which are connected to experiment and spectroscopy. That's why spectroscopy came first, quantum came later. Statistical mechanics on the other hand, you have to do a lot of work, go through the whole postulates, which is certainly far more non-trivial than writing down Schrodinger equation. Of course, if you go how Schrodinger did it, in his original paper, if you read, it will be a lot of fun, that how he argued, which was given in the first edition of Berry, Rice and Ross. I used to have all his original papers at one time. That's what I knew that he did everything. He did it from de Broglie wavelength, de Broglie hypothesis. He does not do that operator equal, that was done by Dirac. His history is very interesting. So there was a formidable thing that went on, photoelectric effect, black body radiation, Planck's, that led to quantum mechanics. Here the Maxwell, then Boltzmann, but Boltzmann is so difficult we cannot work out Boltzmann's equations in a class. So we start with Maxwell, then okay, Boltzmann tried and did S equal to KBL and omega. Then comes the Gibbs, this formidable wall of the postulates, microcanonical, canonical, grand canonical. Then you come to applications. But the first applications are actually the fluctuations, which just the, I think one of the, and the linear response. That is one of the most fundamental thing of natural science is the response functions that we will be able to do tomorrow.